right? Means the material is more resistant to bending, right? Let's say you change the center part to steel, and then the width is still the same. The structure is more resistant to bending. To make it equivalent, right? To make it equivalent, the word down here is equivalent. What must we do? We change it. We have to halve its size, okay? Because based on Young's modulus, as you can see up here, based on Young's modulus, it is half. That's why you halve the width. Now, I'll give you another. So case number 2. Okay, so what we do now, case number 2. Anyone, any questions so far? Anyone? We okay? Okay, so let's look at case number 2. Okay, so what I'm going to do is case number 2. What would be the benefit of having two different materials? So one was a question is that, so is basically lightweight. Okay, so make it lightweight, right? So if you make the whole thing out of brass, okay, your weight is lighter. However, brass is very soft, so you put a steel on top. And then another question is the small end different from the big end in the second moment area? Small end and big end, they're the same end, okay? There's no small end or big end, okay? So sorry. And okay, right. So next one, so let's say case number 2 now. Okay, case number 2. I changed the reference material. Okay. Right. Okay, reference material now is equal to brass. Okay. So we do the same calculation, right? So N of steel. And because brass is a reference material now, so steel, the bottom part now is E of brass. So this will be equal to 2, right? And then the reference material, the N of brass, is equal to E, Young's modulus of brass, divided by Young's modulus of brass. Now this will become 1. Okay. So for this case, we did not change the size. We did not change the size of the brass. Okay. So we use our reference material to become brass. Okay. So now the reference material is brass. So brass, I drew earlier 6 squares. Okay. 3, 6. Okay. So the height did not change, as you can see, right? You can see the height did not change. So this is 1, 2, 3, 4, 5, 6 squares, right? So that's why this is 1, 2, 3, 4, 5, 6. So it did not change. So now brass, sorry. So now brass is the reference material. Okay. Now to make the structure, so now you change everything to brass. So now the top plate and the bottom plate, you also change to brass. In order to do that and to ensure that the structure have the same strength, okay, so what we tend to do, so from here we have to double the length, the width of what? Of brass. Right? We double it. Okay. Why double it? Because it's relative to its what? It's relative to its Young's modulus. Okay. So now this is brass. And then this is brass. Okay. So either way, your answer will be the same. Right? You can see from here. Your Young's mod, your second moment of area will what? Will change. Okay. Your second moment of area will change. Okay. So now if we have a structure now, let's say now the structure does not look like this anymore. Okay. Let's say now I'm going to flip the structure around. Okay. What do I mean by that? So now let's say now the structure looks like this now. Okay. So the structure now look like this. So 2. Right. And then this is 4, right? 2. Right? So now this is, so I will declare that this is your brass. Oh, okay, I will not make it too confusing. So this is steel, this is brass, this is steel. Right? So now if everything is made of, if everything we change to and okay, so now everything changed to reference material now. Okay, reference material now is steel, right? So reference now material is steel, right? So we change everything to steel. Now your structure will look like this. Now your structure will look like this. Now your structure will look like this. Now all is steel. Okay. So what you realize is the height did not change, only the thickness changed. So this is the brass equivalent to steel. You change everything to steel. Now, if the next one is a reference material, is brass, right? So now the reference material is brass. Okay, so what will happen is all will become brass. Okay, and then the thickness will what? Will change. Again, an important thing to emphasize over here is the height did not what? The height did not change. Okay, a big thing that I'm going to emphasize down here is the height did not change. Only the width changed. So this is brass. This is steel equivalent to brass. And the other side, right, is the same thing. Okay, so this side is a steel equivalent to brass. Okay, and I'll put down here for all of you, note only the width changes and height is held constant. Okay, I think this is important. And why is that? Is because of your second moment of area. Okay, now a term that I want you all to look at is NA. You guys will say, Eugene, so if it's NA, so what are we changing? Right? So if we look at area, so this is equal to N, right? Width and diameter. Okay, so the concept still works. What do I mean by the width is changing? Okay, the depth onto held constant. Okay, right. Anyone, any questions so far on this aspect? You have to grasp this first. Then you understand when we start doing different material, 2, 3, sometimes can be 4 materials. The only thing that we change is the what? The width. The only thing that we modify is the width. Okay. Anyone, any questions so far? Are we okay? Okay. Now let's look at one example. I don't hear anything. So I've put all these example on Avenue to Learn. I hope you guys have downloaded it. So this is our example. Okay, we're going to do one problem on this. Okay, so this is example number 1. Okay, so if you look at the example, the top plate is made of aluminum and is used to reinforce a Kevlar 49 plastic beam. Determine the maximum stress in the aluminum and in the Kevlar if the beam is subjected to a moment of 900 pound-feet of moments. Okay, so we have a moment. Okay, you can see a moment down here. So like what I taught last week on the recorded video. Last week, I know the recorded video, the notes are very, it's not a lot of notes, okay, but there are concepts that I want you all to follow. So one of these concepts, just to make you guys recall, if you look at the moment arrow, right? I hope you all can see the moment arrow. Over here is the tail end of the arrow, and we know that at the tail end, you'll be under tensile. The head end of the arrow, as you can see, you know, at the top will be under compression. Okay, so depending on the location of the centroid, certain region is in compression, certain region is under tension. Okay, so this is one thing that I hope you all will embrace and recall. Right. So now, so we have two materials, right? So I'm going to write down. This is not given. Okay, you have to find this out. That the Young's modulus of aluminum is equal to 10.6 times 10 to the power 3 psi. Okay. Then the Young's modulus of Kevlar. Okay, Kevlar is equal to 19.0 times 10 to the power 3 psi. So we know from here Kevlar has highest Young's modulus. So for this case, okay, we deliberately pick the reference material to be aluminum. Okay. Now, any reference material you pick, the answer will be the same in terms of stresses. I repeat again, in terms of stresses, your numbers will always be the same. Okay. So immediately you can apply the first formula that we have done. So we know that the N, before we do anything, okay? So what we are trying to achieve down here is to find second moment of area. Okay, so I, okay, so before we do I, on this case, okay, I'm going to draw our transformation. Okay, transformation is important. So this is our transformation axis. So this is my x-axis. Why x-axis is along this way is because it's along the length of the structure, right? So this is the y, and this is the z. Okay, so because of the moment, okay, the moment is going this way, right? So this axis over here is in the what? It's parallel to the z-axis. So what we are trying to achieve here, right? Before we go on, what I'm trying to achieve here is we still want to find the stress in the what? X direction. Okay, and then the because it's composite material, we have to find out N over here, right? And then multiply by mz over izz multiplied by y. Okay, so this is different from shear stress. Remember shear stress, what we have, right? Shear, right? When this is V in the Z direction, this is divided by what? Iyy qy divided by T. Now, there is shear. Now, this is normal stress. It's different now. If moment is in the Z direction, right? If moment is in the Z direction, you have to use what? IZZ, okay, multiplied by Y, okay? So it is different. So now the thing is this, okay? What is this IZZ? So in order to calculate IZZ, right? In order to calculate IZZ,